All right, everybody, this is it. Final lecture class. How did this happen? How did we come to this? Time is how that happened. I would agree with that. But it was like, it's never going to get here. We're never going to get to the end. And then all of a sudden, we're just there. It's kind of weird. So I have a number of things I still want to talk about today, mostly conceptual. I will let you know kind of when we leave the realm of equations you have to worry about and maybe have to know how to deal with, all right? There's a few equations I want to give you on this particular set of slides, and then most of the next chapter is just conceptual because I want to sort of pull the semester together and make you feel like you learned something that's connected to something, okay? If you haven't felt that, maybe already. There have been some times where it seemed really theoretical, and maybe some other times where you're like, oh, okay, I've heard about that before. I've seen that. I've used that thing before, and maybe it felt connected. Hopefully we can pull it all together a little bit at the end. Also at the end, I'm going to tell you a little bit about the exam. And then later, like in an announcement, in a couple days, I'm going to tell you even more about the exam, which is going to be fantastic. Okay. I can't tell you today because I don't know yet. Once I know the answers, I will tell you the things that I'm going to tell you. How's that for vague? Maybe a little bit. All right, so AC circuits is what we're talking about. We dealt with resistors. The idea is resistors with an AC current, they're just resistors. They don't really care all that much. Capacitors behave a little differently because now we're sort of sloshing the current and the charges back and forth. That gap in the capacitor doesn't really matter anymore, but we end up in this situation where it's like I send some current and it takes a little while for the charge to get there and build up. But before it builds up very far, I send the current the other way and I start removing charge and send it the other direction. So we get a case where I have an applied current that is oscillating, alternating current, and we also get an oscillating voltage across the capacitor that's delayed. It's delayed by 1/4 of a complete cycle. What we didn't get to was a little bit of a new version of Ohm's law that looks something like this. I'm going to write it two different ways. First of all, VO is equal to IO times X sub C. Notice there I'm using peak voltage and peak current, the maximum they ever get to in the circuit. Or you can write this in terms of RMS values. But the new thing is that X sub C that you see over on the side. Notice where it sits in what really looks a whole lot like Ohm's law. It sits where the resistance was before, okay? So this X sub C can be thought of as, let's call it opposition to alternating current from a capacitor. So I'm trying to avoid using the word resistance because it behaves like a resistance, but think of it as something that's trying to oppose alternating current, and it's specifically the type of opposition that comes from a capacitor. It has a name. It is known as, and prepare yourself for some terms today that can easily get jumbled in your head, all right? This is known as capacitive reactance. Capacitive reactance. And it turns out, let me give myself a little more space here if I can. Let's try this. Move that over. Come back. Thank you. Okay, and this X sub C has an equation of its own. It is equal to 1 over omega C, and omega is always equal to 2 pi times the frequency. So 2 pi times the frequency of the oscillations of the alternating current times the capacitance that's there. Which means that the amount of opposition that the capacitor puts up is dependent on the frequency of the alternating current. It's not like a resistor where you can just look at the side of it, look at the little colored bands, and it's like the resistance is this much, and it's always this much. Now I'm going to have a capacitor that, yes, might have a certain fixed capacitance, but it puts up different amounts of opposition depending on how quickly I oscillate the current back and forth. Yes?
So does that mean that if you oscillate it fast enough,
Yeah, exactly. So if we make the frequency high frequencies, less opposition. And if you think about the capacitor, it's like it kind of likes that behavior, right? The fact that it has that gap, the more I switch back and forth really quickly, the more I'm sort of avoiding that gap that sits in the middle of the capacitor. So it puts up less opposition. If I go the other way and I go to frequency 0, frequency 0 is direct current. It means it's not oscillating, it's just, there's the current. It's just passing through, and we know that the capacitor will charge, quit charging, and then there will be no current. In other words, it puts up infinite opposition to DC current. Okay? Do you see how this sort of relates to the behavior of a capacitor and goes back to direct current and fits? Yes. Should we write those couple things down? Maybe. Okay? So let's see. F equals 0. I don't have much room here. XC is infinite. And F high, XC, is low. So less opposition to higher frequency alternating current. Now, if we take these same ideas and imagine how inductors behave, we can get sort of the same kind of concepts for inductors in alternating current circuits. And it turns out in this particular case, you have to remember the idea that inductors oppose change. So when it comes to like direct current, when it's not oscillating, that's like an inductor's dream, right? It's just like send the current through. It's like, the current is staying the same all the time. I like this. It puts up no opposition at all to that, okay? Of course, it really doesn't serve any purpose then either, because it's just a coil of wire and current's passing through. Yay, that's not terribly exciting. What you might imagine that the inductor dislikes is when I change the current faster and faster and faster. In fact, the faster I oscillate the current, the more opposition the inductor puts up, okay? And again, we get that from the idea that inductors oppose change. So let's talk about the equation first, and then I'll give you that graph to show you how these things vary with each other. So we can write, once again, VO is equal to IO times X sub L this time, or you can write the same equation with RMS values. And this X sub L is known as the inductive reactance. And the definition applies there as well. It's essentially opposition that's coming from the inductor, and it sits in Ohm's law in the place of the resistance. It has an equation of its own as well. It is equal to omega times L, which is the same as 2 pi times the frequency times L. So notice what happens this time. If the frequency is 0, well, then X sub L is 0, okay? If I don't oscillate, the inductor just says, great, this is fantastic. I don't care, do what you want to do, right? If, on the other hand, the frequency is high, they are directly proportional, so the inductive reactance will be high. It will oppose alternating currents with higher frequencies. I should also let you know that because this sits in the equation in the same place as resistance, it has the exact same units. So let's put that there as well. It's in ohms, and over here, this is in ohms, okay? Just like with resistance, it's measured in ohms. So this time, let's look at these two peaks. Let's talk about an applied voltage. In other words, I have a potential difference that's being applied by the alternating current source. It's saying go current, all right? The inductor is going to immediately say no thank you, all right? Notice its current is 0, the current that's passing through the inductor, but then it begins to lose and give way as the current grows, but at the same time, the voltage is dropping. As soon as the voltage goes to 0 and begins to go the other way, that's the point where the current's not going to get any larger. It wouldn't make any sense for me to continue to have more and more negative potential the other way and for this current to continue to grow. So that begins to bring it back down. But you can see, once again, these are offset from each other by 1/4 of a complete cycle. One of them is at 0 while the other one is at a peak. So the applied voltage is given there, and we can say that the current through the inductor is 1/4 of a cycle behind. Again, they are out of phase. They are out of phase by 1/4 of a cycle, and it happens because the inductor doesn't like change and it sort of stalls a little bit. Okay? So what can we do with all this? Basically, the remainder of this chapter, I think I have like 2 slides that are left here, which kind of relate to 2 different applications. First of all, I don't know if any of you have at any point in your life been into like audio systems. Back in the day, it was like really big that like everyone was like, I'm going to put huge speakers in my car. And then like, I don't know, it feels like it's kind of fallen out of fashion some, maybe not, maybe in different areas of the country, different groups, everything's a little different. I just know that there used to be like car stereo shops everywhere, and now you don't really see them. So, it seems to have fallen by the wayside a little bit. But, a lot of people are still into high-end audio in their home. A lot of people just listen to earbuds all the time, and that's perfectly good enough, all right? Same ideas apply, though. Let's talk about, we have a speaker that's sitting right here. If we were to take the front of that off, you're probably going to see 2 smaller speakers inside, maybe 3. I would guess, looking at that, I can't quite see through it. There's probably 2 up there, all right? So it might look something like this. Each one of these cones is a speaker in and of itself that's designed to play a certain frequency or a certain range of frequencies of music and do it well, all right? So this one at the bottom, the one that is larger, it's going to be heavier, first of all, just because it's bigger, which means it's not really built to move really fast. But simultaneously, because it's bigger, it can oscillate more air. So it's going to be something that perhaps you can feel a little bit more. On the other hand, the one at the top, because it's smaller, it's often built with really, really lightweight materials as well, so that it can oscillate really, really fast. So the one at the bottom is built more toward lower frequencies, more toward bass. And if it's built really, really well, like maybe it can move enough air that you can feel the vibrations, okay? The one at the top, since it vibrates really, really fast, it's for the higher frequencies. So what you would like to do is take like a complicated audio signal that is a mixture of like all sorts of frequencies, from really low to really high and everything in between, and say, okay, I want to take this music and send the appropriate frequencies to the speaker that's designed to play them, okay? It doesn't make sense to take something that is a really high frequency sound and send it to something that can't even move back and forth really quickly, okay? It's not going to do a good job. It's not going to faithfully reproduce the sound, and vice versa, okay? So what we do is we use a circuit that has both a capacitor in it and an inductor in it, and we send the music just straight at both of those, and they're going to act as filters, essentially. Remember on those previous 2 slides, we said that high frequencies, as you can see here, high frequencies result in a lot of opposition. Okay, high frequencies see a lot of opposition from an inductor, and the opposite is true for a capacitor. So, if I want to have something that plays low frequencies, which, by the way, is known as a woofer, which, yes, is a funny word, and if it plays extra low frequencies, you might even call it a subwoofer, all right, is the larger speaker at the bottom. So what I do is I put an inductor in the way, and it's going to get rid of the high frequencies. In other words, the only thing that's going to get, the only part of the music that makes it to this speaker are the low frequencies, and it's designed to play them, so it'll do a good job, okay? On the other hand, the tweeter, the one at the top, since it's designed for playing high frequencies, notice they've even drawn it there, we put a capacitor in the way, which according to the equations we had before, will block the lower frequencies and let the other ones through. And then this one will only play the music with the higher frequencies. better and better sound systems will break this up even further, and it'll be like, oh, I need one speaker that only plays the really low stuff, and another speaker that plays the stuff that's a little bit higher, and another speaker that plays the stuff that's a little bit higher, and each one is specially fashioned to play those frequencies, and it sounds more lifelike, it sounds more realistic, it sounds more impressive overall, okay? Yes?
So ultimately this goes back to that, like saying the path of least resistance is what kind of decides how each one goes into each speaker.
It's kind of the path of least resistance, yeah. It's not only the path of least resistance, it's literally that, like, some frequencies just can't get through here. So they are completely and totally opposed, and the other way is just easy sailing, okay? And of course, many frequencies, it's kind of, it's like, well, it's half as easy to go to this one as it is to that one. So most of it will get to one speaker and not to the other.
Can you get multiple currents in one, or sorry, multiple frequencies in one input?
Multiple frequencies in one input?
Right, because like a song is built up of several frequencies.
Yeah, like infinite numbers of frequencies, all laid on top of each other. That can all be in that one signal. So it's a lot more complicated than the stuff we've been looking at where we just have, yay, one frequency, okay, that's going through. You can layer as many frequencies on top of this as you want to, and really that's the signal that's inside of that alternating current. It's like alternating current with a complex mixture on top of it, okay? Resistors, inductors, capacitors with alternating current. That's just one application. Another thing is all the way here at the end. What if we put everything together? Okay, we've got alternating current, so it's going back and forth, and we're going to put it in a circuit with a resistor, a capacitor, and an inductor. What happens then? Well, it turns out that, we know that resistance just straight up gives some sort of opposition to the alternating current. And we know that we also have X sub L and X sub C. This is a constant, and these two are dependent on the frequency. How much opposition they put up depends on which frequency is trying to get through, dependent on the frequency. And we have equations for both of those. R is constant, the other two have their own equations. If we combine all of this together, resistance and capacitive and inductive reactance, they all have a name together. It's known as impedance. All forms of opposition put all together in one is known as impedance. So I told you we had some terms today that kind of all stack on top of each other and all sort of sound the same because it's like, 3 or 4 syllables and it's like, yeah, it kind of sounds fancy and it's a word jumble. We have capacitive reactance, inductive reactance, and impedance, okay? A little bit hard to keep straight perhaps. Impedance, as if this doesn't state that we're at the end of the semester, is given the symbol Z. It's like, boom, we are done. Nothing else left to use at that point. All of them added together is given the symbol Z. And it turns out this is the way you combine them. Let me scroll all the way to the end here. Z is equal to the square root of R squared plus omega L minus 1 over omega C. There's your capacitive reactance and inductance, inductive reactance rather, squared. And those are subtracted because you remember one of them was like a quarter of a cycle in front, and the other one was a quarter of a cycle behind. And it ends up they're kind of like in the opposite direction. Where that comes from would have been this slide. We're not going to worry about that, okay? So where that equation comes from is that other slide. I just want to show you that they all come together. So it turns out if we were to graph all three of those, R is a constant, the other two, omega L and 1 over omega C, it looks something like this. Notice this is the impedance from that particular thing, the amount of opposition as I'm increasing the frequency. So R, it's like, well, I don't really care what the frequency is. I'm just the same amount the entire time. On the other hand, XC offers more opposition, more impedance at lower frequencies, and not a lot at higher frequencies like we saw before. And XL offers less opposition at the lower frequencies and more opposition at the higher frequencies. So when I put all three of them in a circuit together and I like change the frequency, there's this weird interplay between the three. It's like they're combining in different ways. R is always there, but the other two are sort of inverse to each other as I go from low frequencies up to high. It reacts differently to different frequencies. So since that equation looks like that and has that minus sign in between the inductive reactance and the capacitive reactance, it means there is a point where they can be equal but opposite in sign. Okay? There is a frequency where these have the same value and they're being subtracted from each other, which means they just cancel each other out completely. They're offering no opposition at all, which leaves only the resistance. Okay? So let's write that down here somewhere. At some frequency, XL and XC cancel out. This will be the point, or let's not say the point, this will be the frequency with the least opposition in the circuit. There is one frequency in the circuit where the opposition, the total amount of impedance, reaches a minimum. Okay? According to Ohm's law, what happens when the opposition is the lowest? What's that? Let's say voltage is constant. If I have an applied voltage and I minimize the opposition, then we get a higher current. Okay? At the point where there's the least amount of opposition, we are going to have the highest current. Okay? And you can see that graph here. This black line at the top, this is Z. This is all three of them added together. And you can see it reaches a minimum amount of opposition that's equal to only the resistance at this frequency where these two cancel each other out. Right? This particular frequency is known as the resonant frequency. The resonant frequency. It's the resonant frequency for that particular circuit. And you can see it written right down here. It has its own equation. For any given circuit, it's equal to 1 over the square root of L times C. Okay? So you build a circuit. It has this one frequency where you're going to get the most current. Now, I'm going to use this slide and also connect it with the last slide of the last chapter. Here's the thing that I want you to take away from this slide right now. Let's imagine that you're actually using a television and not a streaming service for just a second, okay? I know, that's far-fetched. And let's imagine that you have like an antenna, which, by the way, with an antenna, free high-definition broadcasts are just out there available for you and often look better than streaming because of compression that's not there when it's broadcast over the air. So just in case you're interested, all right? What happens is like you want to tune to different channels, essentially, right? You're here, you're like, oh, I want to pick up the NBC signal, or I want to pick up the CBS signal. And you're thinking like, I don't know what you're talking about. I go to Netflix, I pick a show. Like, what is this channel thing? I completely understand your quandary, all right? Well, let's say that maybe on your remote, you're like, boom, I know, I hit that button, it goes to the CBS channel. What is happening? Essentially, there is a circuit in the TV that's a more complicated version of this, okay? When you do that, the circuit changes the capacitance and the inductance in a circuit that receives the signals through the air, and it's changing the resonant frequency to match the broadcast frequency of that channel, which is why the circuit then actually has a current that contains all the information from that TV channel, and it's ignoring all of the other frequencies that might be hitting it at that point. All the other frequencies are experiencing all of this other opposition and they're not doing anything. That one frequency, the resonant frequency of the circuit, matches the broadcast frequency. A current is created in the circuit, and that current contains your television shows, which seems a little far-fetched and magical, right? Okay? So what you're doing is changing the resonant frequency of a circuit when you change the channel, and you should use that terminology from here forward, right? I think, perhaps. Could you please change our resonant frequency to CBS? That's the way you should speak to your roommates, I think, all right? Now, hold this slide in the back of your mind, and let's talk about the last topic of the semester, which is the topic of electromagnetic waves, which, by the way, those broadcast frequencies that are going out, CBS that's broadcast through the air, it is an electromagnetic wave that you have a television that can pick up, okay? So there's going to be a lot of stuff that we skip over quickly and ignore, like these diagrams on the right. If you're kind of giving them the side eye right now, being like, I don't like the looks of that, we're not going to worry about it, all right? And I will admit, even if we had the time to do it, it's kind of out there. So just don't worry. Just bye. See, you never saw those, okay? So here's the thing. This is kind of a summary of what we've learned, wow, like I guess about the whole semester. Lately, we came up with the idea that if I have a magnetic field and it's changing, we get things like an induced magnetic field, a current, and a voltage. It's like it produces that in a circuit, okay? The only way I can ever have current flowing is if there's also an electric field that's there, is another way of thinking about that. So just the fact that a magnetic field is changing, it produces all of this stuff. So you might ask the question of whether that can work backwards. Is it possible for me to take an electric field and change it and get that to make a magnetic field? It sort of makes sense that it should work both ways, and people speculated on that and then did the math and did the test and the experiments, and it turns out it does work both ways. It's like the electric field and the magnetic field. If either one of them is changing, it makes the other one happen, okay? As long as nothing's changing, if I just have a point charge and it's creating a magnetic field and I make sure nothing moves, magnetic fields never happen. It's like I can just pretend the electric field is all by itself. But as soon as that charge moves, something is changing with time, magnetic fields get created, and if magnetic fields are being created, they back create electric fields, and all of a sudden there's this weird interplay between electric fields and magnetic fields. So they are separate if neither one is changing, and intertwined if they are changing, okay? So this is going to go somewhere, believe it or not. First of all, Ampere's law, which was everybody's favorite, we need to go back to that a second. We're not going to do any problems. What I want to do is just say that it makes sense that if electric field is creating a magnetic field, I need to include that in Ampere's law. Ampere's law looked like this the first time we saw it. And I'm sure all of you are like, Ampere's law, yeah, I remember that. Remember, maybe it looked like this, B dot dl is equal to mu naught times I enclosed. It said that moving charges created a magnetic field. It turns out that's not all of Ampere's law. We also need a part in here that tells me that a changing electric field results in a magnetic field as well. So while we didn't learn about it at the time, I just want to write it up here. There's another part of this, mu naught epsilon naught times the rate of change of the electric flux. So here I have an electric field that's changing and it's making a magnetic field. It turns out we don't often talk about this last term because it's like a small effect. It's really small compared to the other one. So try to read this if you can. I know it looks kind of foreign. Moving charges, current, make a magnetic field. Changing electric field creates a magnetic field. Okay, that's what this equation is telling us. So let's hang on to that for a second and get rid of this slide. Okay. Let me also point out that there is something known as Gauss's law for magnetism. We did it with electric fields. You're not going to have to do it with magnetic fields. I just want to write it up here and tell you what it means. And it looks something like this, B dot dA is equal to 0. Gotta love that one. This is Gauss's law for magnetism. And essentially what it says, remember what was on the right-hand side of this with electric fields? It was Q enclosed. I could take a Gaussian surface and say, there is a point charge that's making an electric field. This is telling me that there's no analogous thing with magnetic fields. There's not like a point that can create a magnetic field. Remember, magnetic fields are about 2 poles, a north and a south pole, and the magnetic fields loop from north to south and around in a circuit. That is what this thing is telling us. It's saying that, first of all, there is a north and south pole for magnetic fields. It's also telling us that there is no, like what you might call a magnetic charge. Like that's not a thing because I can't like enclose something like that. And it also means there is no isolated pole. I can't split a magnet in half and say, ooh, I've got a north pole and magnetic field is coming out from that. If there is a north, there is a south because the magnetic fields create loops. They don't originate from a point, okay? Once we have those 2 equations, we can get to this, which is kind of what we've been building toward all semester, even without saying it, okay? It's a set of 4 equations, which are in many ways considered like one of the greatest achievements of physics ever, all right? Everything that we've learned, every little piece of thing that we've learned about electricity and magnetism, as well as all the many things that we have not learned about electricity and magnetism are in those 4 equations, which seems weird. I know, you might be thinking like, what about this equation we had? Whatever equation we've had this semester for whatever particular situation, there is a way to get from these 4 equations to that specific thing, okay? So if we were going to be like, I don't know, like a PhD level electricity and magnetism class, what we might say is just like, okay, like you're about to have an exam, any question is valid, you're allowed to bring these 4 equations with you. Like you should be able to get from there to anything in electricity and magnetism without bringing anything else in, which is kind of crazy, right? 4 equations to rule them all, which is kind of nice. It turns out that these are even considered more fundamental than Newton's laws, which we think of as like, whoa, Newton's laws, those are a big deal. Because Newton's laws kind of break down. If you go too fast or have too much mass, Newton's laws don't work anymore. They have to be corrected. These work in every situation we can find. So they even work at really high speeds and with really great distances and with really large masses. In other words, it works with relativity as well, if you're kind of getting the drift of what I'm talking about there. If you look through these, you might be thinking like, oh, I don't know what that is. And then you start to say, wait a minute, I've seen these equations before, right? We've done these. This was Gauss's law. It was specifically our original Gauss's law for electric fields. I just gave you this one. This was Gauss's law for magnetic fields. What's this one? Does it remind you of anything or even seem kind of similar to something we talked about? What about the right-hand side of that? Magnetic flux changing. What law did we have magnetic flux changing inside of? Maybe this one? The one I talked about on the video lecture that you need to go watch, I think. Okay, Faraday's law. And this is the one we just talked about, which is Ampere's law. Maxwell is the one who put it all together. Okay, Maxwell took all of this, put it together, and showed that, well, everything is encapsulated in these 4 equations. And it turns out he did one other thing. He did some predictions based on these equations. And when I say predictions, I mean, think prophecy, right? It's like, okay, I have a reason to believe based on these equations, which I know are true, that this should be something that exists, okay? Something that we had no proof of, had no idea there was the existence of. He was able to use these equations and say, I believe that at some point in the future, someone will find this. And the thing that was this idea of electromagnetic waves. Nothing, okay? He said, these should exist. I can tell you what they should look like, how they're created, what they should do, but he went his entire life without anybody finding them. 8 years after he died, someone experimentally produced and verified the existence of something known as electromagnetic waves and say, well, he wasn't crazy. He was right all along. But can you imagine going to your grave with that? That would kind of suck, right? It's like, trust me, I know it's real. Somebody please find it. But alas, he was dead before it happened. So I'm sorry, Maxwell. We should all wear like t-shirts in his honor, you know, with the 4 equations on there because, yeah, it's nice work. Anyway, so let's talk about those electromagnetic waves. Bear with me. At this point, by the way, like these equations, like you're going to use them back through in the ways and the little bits that we have throughout the semester. I don't expect you to take this and derive electricity and magnetism or anything. As we go forward from this point, actually all this stuff in this chapter, no problem solving. Okay, we're just talking concepts at this point. In the last chapter, as you can see, there were some equations with frequency and stuff. There's some small problems I could give you there, but nothing terribly long. Think multiple choice, all right? In this chapter, I just want you to be able to answer conceptual multiple choice questions. So, how do we get things known as electromagnetic waves? Did you study waves just in general in 220? Last semester or when you took it, did you have time to get there? I know, it's one of those topics that it's like will it fit or will it not? It's supposed to, maybe it doesn't. So let me back up just a little bit and talk about this statement at the bottom. Waving the end of a string up and down. Imagine there was like a rope that was stretched across the room and I decided to pick the rope up off the floor, right? And then take just the end of the rope and go like this. Like you can kind of imagine what's going to happen, right? Every time I like make a bump in the rope and drop it like this, that like bump in the rope will travel across the rope sideways. So if I just keep going like this, you can imagine there's like waves that are in the rope that are traveling down the rope in that direction. So I oscillate something in one place and that results in the production of a wave in the matter of the rope that's waving across the room. What we can do is basically the same sort of thing, except with charges, okay? So if you look at this little apparatus that they've diagrammed here, let's just focus on that first one. Notice we have something that's oscillating the charges back and forth, so an alternating current. And then I've got sort of a conductor that goes up this way and a conductor that goes down that way. If you are bothered by the fact that it seems like this is not a circuit, because it's like, ooh, I just have 2 conductors stuck out to the 2 sides. What if I took these 2 things and folded them down? What would I have? That would look a lot like a capacitor, right? I would just have 2 conductors and a gap in the middle. So if you think of this and maybe extend it out and imagine it like the capacitor circuit, and think of me sending like the charges to one side and then the charges to the other and then the charges to the other, the fact that the gap isn't there doesn't matter so much, okay? So if we start in a configuration where maybe the top part of this is positively charged and the bottom is negatively charged, electric fields point from the positive to the negative. So if I were to draw the entire electric field here, it would look kind of something like this. It would kind of go around like so. We're just focusing on one point, right down the middle. At that point, the electric field points straight down, okay? We're having to ignore the fact that there's an electric field at all these other places because it just gets too complex and there's no way to draw it, all right? So we're looking at the electric field at that one point. Now you might imagine if like maybe there's a switch here and I like turn this on to make the charges go here and let this be negative, it'll create an electric field here and like a split second later, basically the same electric field will be here, and a split second later, it'll be here, and it'll be here, and it'll be here. It's going to create an electric field in the space around it, but it'll take a really, really small period of time for it to sort of propagate through space, okay? We're just looking at like an instant later, we know we have an electric field that's right there. You can see a little bit later, notice that same electric field, we're looking a little bit farther away, it sort of traveled a little bit. That is exactly the same as this one. What else has changed between these two diagrams? There is another electric field like behind it that's a little bit less, the magnitude is less, and one other thing has changed. Yeah, notice over here it was like 4 positive charges, now it's only 2. What has changed is that some of these positive charges went down this way and canceled it out. In other words, there's been a current that's passed in that direction, okay? Because there's less charge here now, this electric field is not as strong as it was before. Let's continue with this. Notice the next one. Ooh. No charge on either side, meaning enough current has flowed downward to sort of balance everything out and make it neutral, which results in no electric field right next to it. The previous electric fields that I made have now had enough time to sort of move farther away from the wire, okay? Notice they're playing connect the dots here a little bit. It's starting to have kind of a sinusoidal shape in the magnitude of the electric field, okay? So what happens if we continue the process and start going the other direction with the current? Notice now we're starting to have a buildup of positive charges on the bottom. So it started with the current sort of sloshing down, and now it's going to start the process of going the opposite direction, okay? Well, when that happens, notice from positive to negative, we have the direction of the electric field, and then the buildup of charge gets greater, which means a bigger electric field. And we could just sort of repeat this process of like sending charge up one way, and sending charge down the other way, and sending charge up the other way, and notice all of a sudden what I'm doing, right? We're right back to like shaking the end of the rope up and down. It's just what we're doing now is it's more like we have charges that we're like sending up and then sending down and then sending up, and we're doing that really, really rapidly. And that's creating an electric field that's changing in magnitude and changing in direction in a sinusoidal fashion that matches the sinusoidal change in the current that's going up and down. Do you kind of at least, can you almost like touch what was explained there? That's kind of all I need at this point. You're kind of like, I kind of maybe see what you're saying. Maybe if I don't have all the details. Okay, but we're going to go into this a little bit further. It may make more sense as we go. So now we're going to look, this is the exact same apparatus. We're just going to zoom out a little bit, okay? And we're going to look at, hold on, whoa, which one is which? I'm confused. A, B, 31.6, 31.7. Okay, I think I've got it, all right? So notice, in this first case, they're showing current going this way, which is causing the buildup of positive charge at the top, which means the electric field points down that direction. But think about current creating magnetic fields, right? Thumb in the direction of the current. That means I get a magnetic field that wraps around this way. Notice the little blue circles. See, on this side, the magnetic field is going into the screen. On this side, it's coming out of the screen. So at the same time I have this weird electric field that's like looping down that way, I have a magnetic field that's going around like this. Which means it's really hard to both explain these diagrams and also to draw them in the first place, all right? Is there a good diagram? Who in the world knows, okay? So we have electric field down like this, that again, remember it's like growing in strength and decreasing in strength, and growing in strength and decreasing in strength. And simultaneously, I have a magnetic field going around like this that's getting stronger and weaker and stronger and weaker and stronger and weaker. And those things are sort of like playing off of each other in a way, okay? If we continue to zoom out a little bit over here and wait a little bit, notice what I have over in this segment. This matches what we started with, okay, with the electric field pointing down and the magnetic field pointing away from you. Electric field pointing down, magnetic field pointing away from you. This is like this part has traveled a little farther away, and now the current has flipped directions, so I'm getting everything in the opposite direction being created now. Notice now the electric fields are up, and the magnetic field is pointing towards you, okay? As time continues to go forward, and I continue to like send the current up and down here, I'm gonna continue to get electric and magnetic fields that are changing direction and magnitude. And that's gonna keep sort of propagating outward, okay? All of that, again, is happening because just like the end of the rope, I'm taking charges and making them go up and down, and that's creating waves that are traveling through space, all right? Let's continue with that idea. So, we're gonna focus on one little piece. Here's the exact same thing we had before. Notice the little piece of stuff that we were looking at kind of zoomed in before. These are the different electric and magnetic fields that are propagating out, and what we're going to do is just look at a slice sort of right down the middle, okay? Because what's happening there is not happening in one direction, it's happening in 3 dimensions in all directions around that charge being whipped up and down, okay? So, first of all, imagine trying to draw that in 3 dimensions, and yeah, it gets messy. I tried to find illustrations online that clearly showed that. There just aren't any. I couldn't find anything I liked that, so yeah, alas, that is what it is. So if we just take a slice right down the middle and then get far enough away from the antenna, we get something that looks like this in its most basic form. We have electric fields here that are up at the same time that the magnetic fields are pointing out, and then they flip directions. Electric fields down, magnetic fields in. And again, this is just what it looks like right in the little middle, straight away from the source, the thing that's creating all of this, okay? That same thing is happening in all directions at the same time. If I just look at that little slice in the middle, that's kind of what it looks like. Big, huge air quotes around that, all right? Notice, somewhere back here was charges that are going up and down. What that creates is electric fields that are changing like this, while simultaneously and perpendicular to that, we have magnetic fields that are growing and shrinking and changing directions. Okay? Your question.
Are the magnitudes the same?
No, not necessarily. Yeah, illustration purposes only. Okay? This kind of makes it look like the electromagnetic wave is like a beam that goes straight along the x-axis. That's not what's happening, okay? These are the directions and strengths of the magnetic and electric field at points along this axis. We just have to draw them out in space a little bit so you can get a feel for what's there. What's happening is this is just what's happening right along the x-axis. Keep in mind there's something that looks very similar to this, just a little bit off from the x-axis. And then there's another one that's just a little bit farther off from the x-axis, and do that in 3 dimensions all the way around, okay? So this is just a tiny little slice of what's happening. Are we still alive? Yeah, it's kind of heavy, right? But this is what we've been working toward all along. I thought I saw questions about to happen. They went halfway there, but not quite. Okay? So let me take this just a smidge further. Remember these equations? We are not going to do this. Okay? You see this thing up at the top? They've taken like a little slice of that wave and like a little loop, and they are going to apply these equations using the tools kind of like we've done before with like Ampere's law and Gauss's law, where we took a little loop and did a bunch of stuff. Let me just point out that if we wanted to do that, hold on. That starts here, okay? Let's use Maxwell's equation to study this wave. Blah, 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 there's the 4 equations, and then you do some stuff, and then you do some more stuff, and then you do some other stuff, and then you do some other stuff, and then la-di-da-di-da-di, it all ends, first of all, with this, believe it or not. The velocity of the wave, how fast it goes, is just the ratio of the electric field to the magnetic field. That's kind of strange, first of all. And then if you go a little bit further, you end up with an equation that looks like this, that the velocity of the wave is 1 over mu naught, one of our constants we've been using a lot, times epsilon naught, the other constant we've been using a lot, and then take a square root, okay? If you do that and plug those numbers in like we've had all along, you get a number that you should be somewhat familiar with. Yes, 3 times 10 to the 8th meters per second. What's known as the speed of light in general. More broadly, it is the speed of propagation of electromagnetic waves of all types. So here's what Maxwell did that was kind of cool. Maxwell took the equations, right? He did basically that work that was on those 2 screens of a bunch of stuff. And then he said, ooh, I think I've found what the velocity of these waves should be. And he found that number. Well, we knew about light at the time. People, like visible light, like of course people have known about light forever. They'd even measured how fast light travels by doing some very difficult experiments by like shining a lantern from like one mountain to the other and somehow like timing how long it took the light to get there. They knew that this was the speed of light. So what does Maxwell say? Wait a minute, that's the same speed as these theoretical electromagnetic waves that we've never seen before. What's the connection? Light must be one of these waves I'm predicting. Light must be an electromagnetic wave, but nobody could prove it until after it was dead, which is kind of sad. But you got to admit, like in a basement in a dark room by candlelight one night, like coming up with this, like doing all of this math that we're looking at today, and then all of a sudden being like, 3 times 10 to the 8th. I've seen that number before. That would be creepy. I bet he like got chill bumps and probably passed out. And then someone came and dumped water on him and said, Maxwell, sir, what is wrong? And, and he's like, 3 times 10 to the 8th. And he passed out again. I don't know. Who in the world knows what happened? Anyway, I like the fact that this number that is so famous ties back to these 2 constants that have been kind of creeping us out all along. And it gives us the speed of the electromagnetic waves. All right? So let me hop back over to here. And again, say that we're not actually going to do this derivation because I don't think you want to. But I do want to point out, and we're doing good on time, we're going to finish 10 minutes early. Isn't that fantastic? Yes?
Just going back 2 slides, I noticed that it's telling us a right-hand rule for the direction of propagation.
Yeah.
Do you need to know that?
You don't need to know that. No. But you're right. You can do E cross B, and it gives you the direction of the wave. But no, I do not expect you to know that. In case you're unaware, a lot of you should be aware of this, but if you're not, light, we just said, visible light that is an electromagnetic wave. It's a combination of electric and magnetic fields that are changing in the way we just talked about. But that is only one little tiny slice of all of the possibilities of electromagnetic waves, okay? All of these other things that we hear about, from radio to gamma rays, X-rays, ultraviolet rays, infrared, and microwaves. Microwaves, that's kind of fun. Satellite TV and the cell phones, and hiding kind of right in here somewhere too, Wi-Fi. All of this kind of stuff is no different than the light we can see. The only difference is how fast the oscillations are, okay? They're all the exact same physical thing. So, think about visible light and think about how much danger is inherently in visible light. Like, there's light in the room right now, and I don't think any of us even think twice if I happen to put my head in front of the projector. You're not like, the light's gonna kill you, right? You don't like imagine that that's something that's gonna be damaging to me, okay? Use that kind of as your baseline as you think about it. And, well, of course, there's other things at play, like what if that light was like crazy intense? Well, of course, like if I ramp the intensity way up, that's changing another factor, and then maybe like, I don't know, I go blind because it's too bright, okay? But inherent invisible light, we don't worry about this hurting us, okay? Notice what's on two sides of this. Ultraviolet light, we worry about that, right? UV rays from the sun, it's some of the electromagnetic waves that's hitting us, and we know that they will burn us. They will cause cancer, right? Take a look. Frequency, more frequency means more energy. Higher frequency means more energy, and if you think about it just in terms of the rope waving up and down, right? This doesn't take a lot of energy. That does, okay? More quick oscillations mean more energy is in those waves. So we worry about these. Notice on this side, infrared. That's like the remote control that you point at the television, right? I don't think anybody's like, step aside, I'm going to change the channel. No one's creeped out about that. Stuff to this side, you can worry less about. Now, don't take that to say that there's no fear, no worry, because like I say, you can change the intensity. Maybe if the intensity's off the charts, you can cause issues. We don't worry about the beam from your remote control. We don't worry about the fact that there are radio stations that are going through our bodies right now, right? Notice they're on a lower energy side from the light we look at every day. In fact, they are much lower energy. Cell phones? There have been no definitive studies that say that cell phones are a health risk, and there shouldn't be a health risk based on this, even though there's a lot of fear and worry and all the things about it. And again, do you want to live on a cell tower? Probably not, because in that case, we're taking something that is relatively low energy compared to visible light, but we're giving you a lot of it. Like the intensity is really, really high because they're trying to take this signal and make it go many miles. So you really don't want to be on the source of that, okay? But as far as receiving it from your phone and sending it back to the tower, that's really low energy stuff. It shouldn't be a problem, all right? Look at the scary things over here, right? We're scared of x-rays. That makes sense. You don't want to just go live in an x-ray machine. You get cancer, okay? Gamma rays, bad things from space, really, really high energy waves. You don't want to get hit with those. So again, use visible light as kind of your benchmark, all right? Let's see, which brings me to one other thing. I don't want to do this. One more slide, all right? I don't want to do this. I don't even want to do this, but I do want to do this last slide, okay? Think about what we talked about in this chapter in reverse, and then compare it to the last slide of the last chapter. Notice what they've drawn here. Just part of an electromagnetic wave. They've only drawn the electric field part of it. And then they show it coming and hitting the same apparatus that we used to create it, okay? So imagine this as an antenna. It's just like sitting there. It's just a piece of metal. Charges aren't moving. But then an electromagnetic wave washes over it. You can imagine those charges are going to feel forces that correspond to the electric and magnetic fields that are hitting it. So connect those two things together. Let me go back to this. Whoa, 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 whoa. We started with that. We make the charges shake up and down in a certain way. We can create the wave. On the other end of it, we can just passively let the exact same apparatus sit there, and those same waves can hit it. And now in here, that will make the charges go up and down just like the creation of them before, which means I can create and receive those signals using the electromagnetic wave in the middle as sort of a connection, okay? What do you connect this apparatus to but a circuit that looks like this? So imagine like we get rid of this thing, and let's just do something, let's get rid of all this. Let's just like connect this to, like an antenna. Like so. So this is like my antenna now, okay? Now I just have a circuit that's sitting there with a resistor, a capacitor, an inductor, and let's let an electromagnetic wave hit that. It will create charges and current moving in the circuit, just like in the circuit that originally created it. And if it turns out the frequency that's incoming matches this resonant frequency, then I get a current in the circuit and I can extract the information that's in that wave, okay? The stuff that's in these last two chapters is like modern society in a nutshell, in a way. The technologies we just take for granted all the time, these 2 chapters. Want to go build the rest of your career and like get into that field? We are in Silicon Valley, right? Like learn how all this stuff works, okay? Your question, and then we're done.
Does that mean that we can power a circuit with?
It is being powered. It's just a really low current that you're getting out of it. So we would have to connect that to an amplifier to actually be able to see the signal and get something reasonable.
If you had enough of an intensity.
The higher the intensity, the more current you're going to get. So, go set one of those right next to the cell phone tower and see what happens. Maybe the current would be a little more than you wanted. Okay? Now, a couple of things. I promised I'd tell you some stuff about the exam. Okay? It will be, first of all, 1 week from today, 1 o'clock. All of this is going to come in an announcement if you just want to listen. I'll send the announcement out later. It will be in this room. I will not be here. I'm sorry. I know. It's kind of sad because something about the final exam gives us all closure with each other in a way. So, but alas, I can't be here. Okay? It covers everything. It will come in 3 parts, 3 equal parts. Part 1 will correspond to midterm 1 material. Part 2, midterm 2 material. Part 3, everything's into midterm 2. I'm going to do my best to make those like equal point values. So like 33% of the test apiece. Okay? Each little part will have some multiple choice and some problem to solve. Here's what's going to come in an announcement later. Okay? For each part, I'm going to tell you how many multiple choice and the problem type to expect. Okay? So if on midterm 1 segment on part 1, if I decide to give you a Gauss's law problem, I will tell you that in advance. Okay? So you're going to know the problems to focus on, but you won't know the multiple choice stuff. Okay? Don't forget as well, for the first 2 parts, for part 1 and part 2, I'm directly going to grade those and say, ooh, did they do better than they did on midterm 1? And if so, it replaces your grade. Okay? That doesn't mean you can just say, I was happy with midterm 1 and 2. I'm just going to do the midterm 3 part. Because then your final exam score is going to suck. Okay? Because all of it together is your final exam score. Right? But at this point, get 100 on the final exam, you've got hundreds for all 3 of your exam grades. I know, which would be fantastic, right? Okay? So, I will stop by saying thank you all for coming. You are the people who come, and thank you for your attention. I appreciate it. Yay, you. Thanks a lot. Good question. Bye.
Do we get a sheet for the final?
Yes, you do get a sheet too, front and back of 1 normal piece of paper. Yes.
Can we get back our cheat sheet from the last term?
Can you, who what?
Get back the cheat sheet from the last
Yes. Let's go next door. I just have a stack of all of them, and you can take yours.
term?